Hi everyone, my name is Rodrigo Cofré. Thank you very much to the organizers of this TopoNets 2020. I'm going to present a joint work that we title High Order Interdependencies in the Aging Brain. This work was mainly carried out by Marilyn Gatica. I'm part of the three PhD advisors of Marilyn, with Patricio Odio and Jesus Cortés. This work is also in collaboration with Pedro Mediano and Fernando Rosas, who developed the main mathematical and computational tools that we use in this work, and Eva Idiez and Stefan Swinen that collect the data and pre-process it. So the brain interdependencies can be studied from the structural anatomical perspective and also from the statistical perspective. While the structural connectivity is naturally pairwise, so white matter fibers goes from one part of the brain to the other, the functional connectivity is not. Nothing prevents you to take interactions among 3 time series or 4 time series, and so on and so forth. So the idea in this work is to go beyond the pairwise functional interactions, or beyond the pairwise correlations, and to consider more complex interactions. And when you consider more than 3 random variables interacting, more interesting phenomena may appear. For instance, synergy and redundancy. And there is a promising tool developed by Fernando and Pedro called OA information that measure the prevalence of synergy and redundancy. So this measure is built from the idea of mutual information that usually measure the interdependency between 2 random variables, the nonlinear interdependency, capture the nonlinear interdependency. And this mutual information can be extended to more than 2 random variables through the interaction information, through the total correlation and dual total correlation, and then there you have the formulas. And something very interesting happens when you take the difference between the total correlation and the dual total correlation. And this is exactly the definition of the O information. We know for 2 random variables that is equal to 0, because the total correlation is equal to the dual total correlation for 2 random variables. And for n equal to 3 is equal to the interaction information. We know that the O information has 2 extremes. One is the extreme redundant example when you have an n-bit copy of the same random variable. And on the other extreme, you have the n XOR, which is the extreme synergy case. And also we know that the O information of 2 independent subsystems is the sum of the 2 O information. So in some sense, what is really measuring is this superposition or the interaction, the intrinsic interaction among many random variables. So we say that the system is redundancy dominated if the O information is positive, and we say that the system is synergy dominated if the O information is negative. So redundancy is this extension of the notion of correlation, and the statistical synergy is this less intuitive process related to emergence, in the sense that it's a property that happened at level n. If you consider groups of n random variables, it's a property that you will not find in any subsystem of n-1, n-2 random variables. So specifically what we did in this example, we took the fMRI data of 164 subjects. We consider a brain parcellation for each of them at the level of 20. So we have 20 time series bold signals for each participant. And we divide the population in 4 subgroups depending on the age. For each of them, we have 20 time series, and we compute the joint probability distribution, the total correlation, and the dual total correlation. So we took also the O information. And we did that for all the subsets of size 3, so all the triplets, all the 4-plets, all the 5-plets for each patient, and then average it for each age group. And when you do that, you find that there are differences in redundancy for all the interaction orders, and the same for the synergy. But the main difference is in redundancy. So in redundancy for all interaction orders, you find that the group 4, so the oldest population, is different than the rest of the population. And this difference is statistically significant even after the correction for false discovery rate. So the oldest population is more redundant. So if you start to look at this information at the level of the modules, so the brain regions, you find that there are 2 types of brain regions, those who are for all interaction orders different in terms of redundancy between the group 4 and the rest of the population. So this is an interesting finding. Another one is that if you take the highest O information value, and then you do that for each brain region, so the n-plet in which each brain region participates for all interaction orders, and you normalize for the highest value of information, you find that the modules 2, 5, and 13 participate at all interaction orders in the most redundant n-plets. So, and remember that the brain regions 2, 5, and 13 are significantly different between the group 4, so the oldest population, and the rest of the population. So something interesting about the modules 2, 5, and 13 is that are constituted by the middle frontal gyrus and the presental gyrus, and specifically the middle frontal gyrus is part of the prefrontal cortex, which mediates executive control and working memory. And the presental gyrus is part of the primary motor cortex, both structures known to be affected by aging. So this is, in this study, we noticed that these brain regions also participate more redundantly in high order interactions when in aging. So if you want to learn more about our work, it's posted on the bioRxiv, and we put also available the code. So if you want to play with your own data with these ideas, it's available in the following URL. Thank you very much.